Welcome to Epic's video on the controlled impedance and its manufacturing process. Um, I'm going to be talking about the the effects of impedance in the manufacturing process and how the impedance is handled and controlled throughout the phases and stages um, of manufacturing. So to start off, you as the engineer and designer of the PCB have in mind your desired impedance tolerance and its own value you want it to reach. Um, Coming and moving that forward into the manufacturing process requires special eyes on the types of variables that come into play whenever we control impedance constraints. There's several factors that come into play, and I'll soon talk about those. So, as a designer, you may specify on a fabrication drawing what you would want your impedance design to be. You will specify, you know, the design, the width, the spacing, the ohm value, and its tolerance. And a general one is shown here. Um, we're looking at a 50 ohm impedance plus or minus 10%, 8 mil line width, and 8.85 mil spacing, coplanar spacing. Um, it's usually not. It's usually common. In fab notes will look just like this with these exact requirements. With some of those requirements, you build a model for your PCB stack up. And in the manufacturing process, we use software tools to build models that tell us exactly what the PCB stack up is going to look like, um, what materials is going to be used, and exactly what impedance constraints we have in the stack up. So, for example, the impedance design we looked at is a single layer impedance on layer one on our top layer. We've got, for example, half ounce copper on that layer. That's going to be a factor in the impedance constraint. So, half ounce copper. Um, the impedance design has or may specify they want to use FR4 material on the stack up, and NetVia's default selection for FR4 materials is Isola's high reliability 185 HR 370 HR. So whenever we use that, though, they have their own dielectric constant requirements that factor a or that play a factor in the impedance calculation. So this model knows of the Isola's 185 HR dielectric constants. It knows our solder mass dielectric constants. We'll see soon that that does play a role, whether you have solder mass on top of your impedance line or not. It has the dielectric constant for the solder mass, the TIO solder mass that we choose to use in the model. Um, the power ground spacing for from the impedance design is known in the model. The pattern of the power ground, if it's a solid plane or if it's crosshatched, does play a role as well, and that's in the model we built here. I'm going to switch over here, and you can see um, I've got two of them here. One of them is going to be designed exact per customer requirements. They've got their design line width, and we're going to simulate the calculated line width per the customer's required design line width, and with their specified ground spacing, um, whether it's crosshatch or no crosshatch on the ground plane, what the ground plane is, and their target impedance homes with their required tolerance. If we to show as a demonstration, the predicted ohms is going to be just barely inside their required tolerance. It's going to shoot for 46.6 ohms. Um, but the design line width can be adjusted to bring that number closer to the nominal value. And that's what this example down here is to show. If we can adjust the line width just a little bit, right here it was bumped up 5/10 of a mil, the predicted ohms gets a lot closer to nominal. And that is then used, and that modification is applied to the CAM software, and that's going to be the next segment.